Let's continue talking about quality of service components. In this case, we're going to talk about queuing and scheduling. First of all, queuing. Queues will store packets after classification. So classification will uh, separate your packets and store them in different queues. So each queue can be provided with different treatments. There is a limited amount of queues. For instance, all hardware only had the capability to handle 2 or 4 queues, but with Catalyst 9000, we have up to 8 queues. You can decide how many queues you're going to use with your Catalyst 9000 depending on your configuration, up to the maximum of 8 queues. Internally, in order to work, queues require buffers. I'm not going to talk about buffering because I already saw that in a different session. But rather than that, I'm going to focus on the queuing and scheduling processes within your Catalyst 9000. So we are going to talk next about IQS, SQS, and AQM. When a packet arrives into your switch, two things can happen. Your packet may be processed by a single ASIC, or it may have to be processed by two different ASICs. The process is hugely different. So I'm going to focus on this process that happens when your incoming packet has to be processed by two different ASICs in order to talk about all the queuing subsystems within the Catalyst 9000. So your packet enters your switch and then it is subject to ingress classification. Your classification will place that packet into a set of queues that are known as two stack queues. This set of queues are managed by a subsystem known as ingress queue and scheduling, or IQS process. So IQS manages all the queuing and scheduling for the two stack queues. Then your packet will have to travel through the stack interface and eventually will reach an egress ASIC where the packet will be placed into a set of queues that are known as from stack queues. The from stack queues are managed by the stack queuing and scheduling process or subsystem that is known as SQS. So SQS is going to manage all the queuing and scheduling for the from stack queues. Then your packet will eventually arrive to your egress port where it will be subject to egress classification, and then that packet will be placed into a set of egress port queues. The egress port queues are managed by the Active Queue Management Subsystem, or AQM. So AQM is in charge of the queuing and scheduling of your egress port queues previous to sending this packet into the transmission line. Let's talk about now what happens if you don't apply a policy map to your interface. If you don't apply a policy map into your interface, you will have only two queues being used, Q0 and Q1, and then you will have a default classification based on DSCCP. This classification will send priority and control traffic into Q0 and all other traffic into Q1. For instance, all traffic marked with EF, for instance, will be placed into Q0. And then your queues will be served by a basic scheduling mechanism. Remember that these are not priority queues. If you want to actually define how your egress, queuing, and scheduling will work, you can use a policy map. You can program this policy map using a modular QoS CLI or MQC. So depending on the amount of class map that you include in your policy map, that will be the amount of queues that you are going to be using at your egress port. So let's place an example here. For instance, let's say that you create a simple policy map that only has one class map. In this case, you are going to use two queues. Two queues because remember that for every single policy map, you are going to use a class default class map. Even if you don't type in this class default when you are creating your policy map, this class default will be created for you automatically. So you will be creating with this policy map that has only class map, you will be actually be using two queues. As you add more class maps into your policy maps, you will be using more queues. Now let's talk about something that is known as port queuing capacity notation or nomenclature. With this notation, you will be able to know how many queues your hardware is capable of providing to you. So you will see a notation like a number and then the letter P, a number and then the letter Q, and a number and then the letter T. The number that precedes the letter P will tell you how many priority queues or low latency queues your hardware is able to offer to you. The number that precedes the letter Q will let you know the number of normal queues that your hardware is able to provide to you, and those queues will be subject to your scheduling algorithm. For instance, weighted round robin. And then the number that precedes the letter T will let you know the number of thresholds available for your normal queues. These thresholds are used when you configure weighted tail drop or weighted random early detection. So, for instance, for Catalyst 9000, we can express the capability of the hardware as a hardware that can support up to 2 priority queues, and then if you use those 2 priority queues, you have other 6 normal queues available for a grand total of 8 queues. So in this manner, you can read this notation for all the Cisco hardware, and in this case, this notation will always let you know how many priority queues you have, how many normal queues you have, and how many thresholds you have available. For instance, this is a list of network cards that you can insert into a Catalyst 6500, and each card will tell you with this notation the amount of priority queues, the amount of normal queues, and the amount of thresholds that it has available for you. So you have to learn to read this notation in order to know how many queues you have available for you for a certain hardware. Finally, let's talk about scheduling. Scheduling is the process or algorithm that will decide which packet to send next. Scheduling is the process or algorithm that will decide which packet to send next. So for instance, let's imagine that you have 2 queues, Q0 and Q1, and each of these queues has one packet ready to get sent into the line. Your scheduling will tell you whether this packet will go first or this packet will go first. That is why we need scheduling. Now remember that Catalyst 9000 have this particular type of queues that are known as priority queues or low latency queues. These priority queues that can be up to 2 will be served first. And then the other rest of queues will be served using a certain algorithm. The most common one is weighted round robin. Remember that your priority queues will operate outside the bounds of the weighted round robin algorithm, and the rest of your queues will use a weighted round robin algorithm to know which packet will get sent next. And this is what we are going to call scheduling. So let's see an example. For instance, in a policy map, you can create your priority queue number 1. If you create a class map and you use this command, priority level 1, and then you can create your priority queue number 2 if you use the priority level 2 command. So you have here your priority queue number 2, and you have here your priority queue number 1. Notice that priority queue number 1 usually is used for voice over IP, and your priority queue number 2 is usually used for video. And then you have your normal queues here. These normal queues here will be served by a weighted round robin algorithm most of the time. This is the most common scheduling algorithm out there. That's it.